Hello, Academy students. Today we will finish up our lessons on electron configuration. I'm going to start with a short recap of what we saw yesterday with the extended and the arrow configurations, and then go into the shortcut for configurations and a couple other things that you can do with electron configurations. We're still looking at standard SC1G, which is dealing with electron configurations for atoms and ions. So starting with a recap of what we saw yesterday, we saw how to write the address, also known as the electron configuration, for any element on the periodic table. Just a reminder that when you look at your periodic table, it is very useful if you label where you can find the different sublevels. So the electrons, the elements that I'm highlighting in red, have their outer electrons in that S sublevel. The ones that I am doing in green, their outer electrons are filling up the P sublevel. Ones that I'm kind of doing in this burgundy-ish color, my transition metals, are my D sublevel. And last but definitely not least, down at the very bottom, my bottom two rows, my inner transition metals make up the F sublevel. Those electrons are going into that part of the cloud at the end. Now, you got to remember that your F and your D sublevels are a little special. They have an extra thing that you have to remember to do. For D, you got to remember to subtract 1 from the period. For F, you have to remember to subtract 2. So what that means is when I go and number my periods and I'm looking at this top row for my D, even though it lines up with 4, it is actually my 3D electrons, and continuing down from there. So this top row lines up with the 6th period, but even though it's the 6th period, there's that overlap that we saw with off-bow, and it's technically our, add Miss Rains, 4F on top and 5F on bottom because of that overlap. So if you have a printed periodic table, make certain you label it. It'll make your life a lot easier when you're looking at doing these electron configurations. So starting with phosphorus, looking at it, I can see that phosphorus has 15 electrons. It is element number 15. That means I need to write the address for all 15. According to off-bow, our electrons always start in that lowest energy level. We always got to start with element number 1, period number 1, and start filling from the closest to the nucleus out. So my first energy level, my first period only has 2 elements, and that lets me know that I get an exponent of 2. It's the S block. So I got to show the sublevel with the letter, and my exponent is saying the number of electrons. After my first 2 electrons, I can look at my periodic table and it gives me a hint that element number 3, electron number 3 is going to go in that second period, and it's going to go in the S sublevel. So we write 2S, and we can count. We're trying to fill all the way up to phosphorus, so I know I'm going to use both electrons. Therefore, it's a 2. I keep right on going. Now I'm on the right side of the table. I'm on the P block. I am still in that second period, though. So it's 2P, and I can count my way through the table. For this row, this part of the table, there are only 6 electrons. Remember back when we first learned about our sublevels, P could only hold at most 6 electrons. So we've done our first 10 electrons. Now we're going to look at electron number 11, and the easy way to do this is to look at element number 11. Element number 11 is in the 3rd period, S block. And if I look on that part of the table, 11 and 12 are both there. So we get an exponent of 2. Now we're going on to the right side of the table. We're still in that 3rd period, but now we're in the P block. And if I count, trying to get all the way to phosphorus, I have to include phosphorus, 3P3. So this is the extended electron configuration for phosphorus. But we also saw how to draw the orbital or the arrow diagram. And it's fairly easy to get once you have that extended configuration because you just give every S one box and then you fill in the arrows for the exponents. So S's have one orbital, one orientation, therefore they get one box. P's have three orbitals, three orientations. So we actually get to see Hund's rule in action here. My electrons are antisocial. They're going to spread out, make their spins as large as possible before they pair up. So now we're at our 3s energy level. Third energy level, S sublevel, it gets one box. And since it's got an exponent of 2, we give it 2 arrows. If you want to write the exponents, you can. I'm not going to count off for extra information. P, again, P sublevel gets 3 boxes. I've got 3 electrons that are going to go in. Got to use Hund's rule, and those electrons are going to spread out before they pair up. We see Hund's rule used. We can actually see it in action with our P, D, and F sublevels. So, before I look at titanium, I want to answer this question because I know y'all have some of your practice that ask you this, and many of the students are missing the words where it says highest occupied energy level. So the highest occupied energy level, we're looking for the biggest big numbers. So for this one, it happens to be 3. I'm going to answer the questions based on what I see written in the blue on the screen. So in blue, I have 0 empty orbitals. There are no boxes that are empty. I have 3 of them that are half filled. That's these P ones right here. They each have 1 electron that is considered half filled, and I've got 1 that is completely filled. That is my S sublevel. I don't include the 2s and the 1s because explicitly I'm asking you for the highest occupied energy level. If I had a box that was empty, I would have an empty one, but for phosphorus, we do not. So let's look at titanium's electron configuration. The nice thing is titanium, element number 22. We can kind of cheat and copy the first part of phosphorus because the first 15 electrons still are going to have to go in the same place. Different cloud, but it's the same organization. So instead of being 3p3, well, we're trying to get to titanium. So I'm actually going to be using all 6 electrons in 3p. So it's 3p6. So now we're at electron number 19. Remember, if you ever lose track of where you are, add up your exponents. My exponents add up to equal 18. That means I'm looking at 19. 19 is in the 4th period, S block, and it can hold 2 electrons. So last but not least, we're trying to get our titanium done. We are at our D block. Yes, we're in that 4th energy level, but we got to remember that it's 1 less. So it's 3D, and I count my electrons. I make certain to include titanium, and it is 3D2. Add up the exponents, double check. It's a great, easy way to see if you did it correctly, because if your exponents add up to the atomic number, that is the correct, most likely the correct electron configuration. It's not a bad habit to get into to double check. Did you subtract from your D sublevel? Did you subtract 2 from your F when we see them? So today we're actually going to look at the shortcut. For our larger elements, it gets really cumbersome when you're trying to write out the electron configuration for over 100 electrons. So there is a shortcut, and it involves your noble gases. So you got to remember that your noble gases are on the right side of the periodic table there, group 18. My noble gases are all in group 18. So the trick to this is that you have to find the noble gas that comes before the element. That's the shortcut. So I'm explicitly looking at tungsten, element number 74 on our periodic table. And I want to know, what is the noble gas that comes before it? Well, the easy way to find the noble gas before any element is to find the element on the table, go up one period, and all the way down to the end. Now, the thing about electron configuration with my noble gases, you never, never, never can abbreviate a noble gas by itself, because it is always the noble gas that comes before the element. So if I was to write the noble gas configuration for my tungsten, I would write XE in brackets. That XE abbreviates 54 electrons. 54 right there in brackets, all nice, neat, and pretty. I would have to write the rest of the configuration. So after 54 comes 6th period, S block, and have a total of 2 electrons. Now be careful when you're doing any ones that are larger than 57, because you don't want to forget your inner transition metals. And they're not on my picture because limited space, but my inner transition metals, 57 through 70, are my F block. And it's 4F because it is 2 less than the row it lines up with. If I was to count, I'm going all the way through it, and on our periodic table, you can easily see that there are 14 columns that make up the F part of the table, so F14. I added my exponents. I can see that I am currently at 70 because I have 54 hidden right here. So 68 and 70, that means I'm looking at 71. So element number 71, we're in the D block. The D is 1 less than the period, so it's not 6, it's 5D. And I count how many electrons to get to tungsten. So 5D4. So notice, instead of writing all of that big old mess that we see up above, we could abbreviate tungsten's electron configuration with xenon in brackets, 6s2, 4f14, and 5d4. Now you got to have the noble gas in brackets, otherwise you're not saying what you think you're saying. If you just skip it and skip straight to 6x without showing that noble gas, you're missing 54 electrons. You're missing those inner electrons, and it's not the element that you think it is. Now, there are tools that can make your life a little bit easier when you're looking at doing electron configurations for elements that are larger than element number 56. This is on page 2 of our cheat sheet. It is the extended periodic table where my F block is actually put in where it belongs. We don't normally show it here because it just takes up way too much space. We still have the rest of the parts of the table just like they normally are. First 2 columns are my S, last 6 columns minus helium are my P's, and my transition metals might be a little bit harder to see, but they are this middle part of the table. Those are my D electrons. Now, this is provided for you when you print out your periodic table. Again, feel free to label it. This is not, but it is a good tool to remind you that my D's drop 1 energy level and my F's drop 2. So we can actually see that overlap, that decrease in energy levels with those harder to get in sublevels. So let's look at a couple. I've got SN 10. To find the noble gas that goes before it, I go to 10, I go up and down to the N. So I would write krypton in brackets. And that abbreviates the first 36 electrons. I then pick up with electron number 37. Element number 37 tells me where electron number 37 lives. It lives in the 5th period S block. and I can see that there are 2 of them here, so it's 5s2. There's no intertransition metals between 38 and 39, so I'm going over to my D block, and I got to remember that it's 1 less, so it's not 5D, it's 4D, and I count my Ds. Now remember that the Ds stop right here. So it is a total of 10 elements. D can only hold 10 electrons because there's only 5 orientations. Sn, we're now at element number 49. Electron number 49, we are now in the P part of the table. So my numbering goes back to normal, 5P, and I tell it how many spaces over, 5P2. I can still check myself. I just have to remember that krypton has 36 electrons. So I take my 36 and I add the 14 that I see. I've got 50 electrons, therefore that configuration is correct. So aluminum, let's find the noble gas before aluminum. I go up and down to the end. So I would write neon in brackets, and then I have to fill in everything else that comes in after neon. So for aluminum, that would be 3s2, 3p1. Remember, I'm getting that from the period and the part of the table that we are in. So last one I'm going to do, and that is Rn. Rn is radon. It is a noble gas, but like we said a minute ago, you cannot abbreviate yourself. It is always the noble gas that comes before the element. And this is element number 86. So I might just want to look at the other periodic table. It might be easier if I look at the periodic table that has the extended one so I don't forget my F's. So I can see that my abbreviation for Rn, I have to start by writing Xe. I can skip the first 54 electrons. One, two, three, 4, 5, 6. Sorry, didn't have it numbered. After that, 55 is in the 6th period. S block, it can hold 2. Now I can easily see my F's. My F's are 2 less, so 4F. Count the number of columns, count the number of parts of that table. Remember, it stops when we get to the next taller part, and it lets you easily see that it's 14 elements, 14 electrons in that part of the table. After F comes my transition metals, my D block. We're still in the 6th period, but D is always 1 less, 5D. And if I counted, I would see that there's a total of 10 electrons here, 5D10. Well, now we're at the last little part of the table. We are officially now in our P block, and we got to count 2 and include Rn, and that would be 6P6. So most students forget about changing the D and F energy levels. That's the most common mistake when you're looking at your noble gas configurations. Either that or they totally forget about the F block. I promise it's part of the table. It's down there. It's hiding, which is why I give you the extended periodic table to kind of look at and help guide you. So that's actually the last of electron configurations. But we can actually use electron configuration to tell some other things about elements. So the first thing we're going to actually do is identify an element from its configuration. I've already actually shown you guys one way to do this. And one way is to add up the exponents. So if you add up all of your exponents, that's going to tell you the number of electrons, that's going to tell you the atomic number, and that's going to tell you where to look on the table. But maybe you want to save yourself some math and not add up all of the exponents. Well, then you can do number 1. And that's basically you look at whatever the last part of the configuration tells you. Now, this only works for ground state configurations. This will not work with excited state that we will see later, but I will specify excited or ground state. So I want to identify something from its configuration, and I want to look at the last piece. Like I said, I could add up all my exponents, and that would be one way to get it, but I want to save a little bit of time. I'm going to 3p4. So I know my p block is on the right side. I know that 3p starts with aluminum. I count over 4, 3p4. This has got to be sulfur. Now, double check, add up those exponents. I've got 10 plus 6 gives me 16. Either way, I get the same answer. So the only thing that would get a little bit tricky is if instead of the extended configuration, we had the noble gas, and I wasn't showing you all of the electrons. Well, just remember that those noble gases are a shortcut. So if I was showing you the short version, add a little extra information. Add the 10 electrons above the neon to remind you that there's 10 here. Well, 10 plus 6 gives me 16. This is still sulfur. So I'm going to pause for a second. You pause the video. Try these for yourself. Pick the method that makes the most sense to you. So example number 1, if I were to add up all the exponents, I would get 42. And that would tell me that I'm looking at element MO, molybdenum. But I also could look at the very last part of the configuration, 4D4. This is 3D. This is 4D. 4D4 tells me I'm going over 4 places. Either way, I get the same answer. So xenon, that's the shortcut for 54 electrons. 54 plus 12 gives me 66. So I've got to be looking at element dy. dy. Yep, not even going to try and say it. But I could just look at that last little piece. 4F is here. Oops, lost the marker. And 4F10, you're going over 10 places. So pick the method that makes the most sense to you. I would say the most mistake-proof is to add up your exponents, especially if you're not comfortable reading that last part of the configuration. So the only thing you got to remember is with the abbreviated, the noble gas configurations, to account for the electrons that are in that abbreviation. So krypton is 36. 36 plus 9 gives me 45. So 4D7 is referring to element number 45, RH. I believe it's ruthenium. Nope, rhodium. Wrong one, rhodium. So that's one thing we can do with our electron configurations. I will give you some and ask you to actually tell me what the element is. Another thing we can do with electron configurations is to determine the number of valence electrons. Remember from earlier in the unit, we saw that valence electrons are the electrons in the outer energy level. They are in that highest occupied shell. The reason we want to know the number of valence electrons is because those are the electrons that actually participate in the bonding. Those are the electrons that are doing all of the chemical reactions that we see. Now, just a reminder that my protons is the identity. So my atomic number determines my protons. My protons determines my atomic number. If the element is neutral, my electrons should equal my protons. My electrons determine my chemical properties. Now, for groups 1, 2, and 13 through 18, it's really, really easy. You look at the last number of the group number, and it'll tell you the valence. But that doesn't account for my transition metals and my intertransition metals. So how do I determine them? Well, the same way I could if I had the electron configuration. So, easy way to do it with my electron configurations is to add up the electrons that are in that highest energy level. So I'm going to write an electron configuration fairly quickly. So 1s2, 2s2, 2p6, 3s2, 3p4. So what's the highest energy level? Remember, my energy level is the big number. So 3 is the biggest. I add these up and I can see that this has 6 valence electrons. It has 6 valence electrons. Well, I could double check by checking the element. This is element number 16. It is sulfur, and elements in the oxygen family in group 16 have 6 valence electrons. So my electron configuration and my periodic table both agree. That means I'm definitely correct. So the nice thing about the noble gases is you don't have the extra stuff throwing you off. You're looking for the highest occupied energy level. So my highest occupied energy level is 5. Add up those exponents, and we can see that this particular element has 6 valence electrons as well. Now I could find the element and look at the group number. So slightly different configuration. Highest occupied energy level is 3. Add up the exponents. This has 8 valence electrons. I could see that this is element argon, and argon is in group 18. Therefore, group 18, that last number, must have 8 valence electrons. So it's the valence electrons for our noble gases, bad Miss Raines, for our transition metals that are a little weird. So transition metals, that D is 1 energy level less. So it's not in the outer energy level. This 6s is my highest energy level used. Therefore, my transition metal here has only 2 valence electrons. You will notice that most transition metals have 2 valence electrons. There are a few exceptions. We'll see a little bit later why they're exceptions, but most of them only have 2 valence. But even though they only have 2 valence, they form a variety of charges, which makes our life very challenging when we get to bonding. So long story short, valence electrons, highest occupied energy level, add up the exponents, that'll tell you what it is. So we're not going to spend too much time on excited state configuration, but we will have a virtual lab where you actually get to see the excited states or what happens with electrons after they are dropping from excited states. So far, we've only been dealing with ground state configurations, and you're only going to be asked to write ground state electron configurations. So this is where the electrons normally are in the atom. But if I were to add heat or energy to an element, I'm going to excite the electrons and they're going to jump up. It could be 1 electron, 2 electrons, it could be a whole bunch of electrons, but they're going to jump up to a different sub-level or energy level. Well, they're up, they're excited, they're where they don't normally belong, and they can only stay there for a little bit amount of time, and then they eventually fall back down. The neat thing is when they fall back down, they give off light. This was, what Bohr used to determine the energy levels, is the light given off by hydrogen when it was excited. But basically what we're looking at is, as a first-year chem student, I'm just wanting you to identify if something is excited. And the easy way to do this is to look at the configurations and see if things are skipped, or if there are zeros in places of where there would normally be numbers. Because basically, excited state, we're looking at electrons where they don't normally belong. They are at a higher energy level. So this is a graphic. I can see that this is one version of our arrow diagram. I like to draw boxes instead of lines, but it's basically telling me the same thing. I can see that this element has 6 electrons. So this is the ground state configuration for carbon. Well, notice this little electron for carbon got all nice and excited when we added that energy, and it moved from here to here. The number of electrons are still the same. This is just the excited state configuration for carbon. If I were to write it, it would look like this: 1s2, 2s1, and 2p3. So notice S isn't correct. We don't have the right number of electrons. This is one way we could see an excited state configuration. I can identify the element just by adding up the electrons. So this element has 6 electrons. It's got some excited somewhere in there, but 6 electrons still tells me it's carbon. Now, you're not going to be asked to write excited state configurations because there's really no way for you to predict which electrons will move or how many will move or how far they will move. But you could be asked to match an excited state configuration to an element or to tell me which element a configuration most likely matches. So let's look at a couple examples. Pause the video, see if you can figure out which ones they represent. So I can see this isn't like normal. So obviously we move some electrons from here to P, but if I add up my exponents, I see that I've got 8 electrons. 8 electrons means this has to be an excited oxygen. This is another way we could see electrons that are excited. Both of the ones from that s orbital moved. They both jumped out of where they normally belong, which is why we're showing 0. And they moved up to 6. So they actually jumped 2 energy levels. They got lots of energy, got really, really excited. Either way, we add up our exponents, and I don't have this typed, so 10, 10, 15, 25. So element number 25 is Mn, manganese. So this is the excited state configuration for manganese. So remember, if you're looking at excited, don't read that last part, add up your exponents. So krypton, I can see that there's a problem here. S is mixing an electron, so I'm going to assume that it jumped from here to P, because P does have a little bit more energy, so it's a little jump. Either way, I need to know how many electrons we have, so I can see that there are 16 by adding up the exponents. But I got to remember that krypton abbreviates 36 of them. So element number 52 is antimony. Antimony, which, yes, its name does not match its symbol. All right, notice our last example, we got a big jump here. So we're not sure which electrons jumped from where they needed to go to up to the 6s, but add up the exponents and we see that we get 38 electrons, if my mental math serves me correct, and 38 electrons is strontium. So, like I said earlier, you're not going to be asked to write excited state configurations. You would just be asked to identify them. Not going to see very many of these, maybe 1, 2 on a test or quiz. Alrighty, last but not least, electron configuration of ions. So you got to remember that metals form cations, and they form those cations by losing electrons. They form those positive charges by losing electrons. My nonmetals, those right side of the periodic table elements, form anions, and those anions have a negative charge because they have went out and stolen electrons. So when you're writing the electron configuration from an ion, there is really 2 ways to deal with it. My preference would be to look at and do this first method. So write your normal configuration and then remove valence electrons for metals or add valence electrons for nonmetals. Method 2 does not work for transition metals. It kind of falls apart with transition metals, but it'll work for anything else. So any of the others, figure out how many electrons it does have and write the configuration for the element that it is pretending to be. Like, for example, magnesium ion. Magnesium forms a +2 ion, which means it has lost 2 electrons. Magnesium normally has 12 electrons, but it lost 2. The magnesium ion has 10. So if I were to write the electron configuration for the magnesium ion, I would basically be writing the electron configuration for neon because they are the same. Magnesium is pretending to be neon. 1s2, 2s2, 2p6. So this would be my electron configuration for magnesium ion. Now you do want to make certain you have memorized the ion that each of the representative elements form. This will make your life a lot easier as we get throughout this course because I expect that students can look at the periodic table and know that certain elements always form certain charges. So remember, we start positive, we count up to 4, and then we flip to negative and we start counting down. Yes, it's related to the valence electrons, but it's also a pattern in itself. So you could just memorize a pattern. So calcium ion, calcium is in group 2, always forms a +2. So I'm going to write its normal electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Calcium is a cation ion. It has lost 2 electrons. Therefore, those last 2 electrons have went away. So I'm going to erase those last 2 electrons. Phosphorus. Phosphorus forms a -3 ion. I'm going to write my electron configuration for normal phosphorus, 1s2, 2s2, 2p6, 3s2, 3p3. So this is what phosphorus normally has, but this phosphorus, it's an anion. It has added 3 more electrons. So instead of being a 3, it is a 6, 3p6. Now, hydrogen is one of the weird ones, as well as silicon and germanium. They can technically go either way. So I would specify either hydrogen +1 or hydrogen -1, or cation or anion. So cat, remember that T reminds me that it is a plus sign. So hydrogen -1, anion, a negative ion, -1. So hydrogen cation, well, its normal configuration is 1s1. A cation has lost an electron. Therefore, the hydrogen cation has 0 electrons. And yes, you could have done the same thing up here. I didn't think about it till just now. You could have wrote 4s0. It says the same thing. No electrons in that outer energy level. Alrighty, so hydrogen anion. Normal hydrogen has 1 anion. We've gained an electron. That's why we have a negative charge. So instead of having 1, it's going to have an exponent of 2. The hydrogen anion is 1s2. Last but not least, I'm doing one of my transition metals because I said these are the ones that kind of get a little wonky. So write my normal configuration, 1s2, 2s2, 2p6, 3s2, need more space, 3p6, 4s2, 3d3. 3. So the electrons that we lose first are the electrons that are in the outer energy level. So vanadium is going to lose these 2 electrons in the 4s because that is the highest energy level before they lose any others. So we've lost those 2, but vanadium being a transition metal, it can form a +2, +3, +4, +5. So vanadium +3, we got rid of 2 of them. We got to lose 1 more electron, so we're going to change that 3d3 to 3d2. I won't have you do very many transition metals, but just kind of know that they lose from that highest energy level. They lose their valence electrons first. Just transition metals get a little bit wonky. So last but not least, and this is really only relevant for students who plan on taking AP Chem or chemistry in college, guys, not everybody follows the rules. All right, we've already seen where hydrogen doesn't always follow the rules. And a couple of our metalloids don't always follow the rules. And helium, even though it's on the right side of the table, is really an S and not a P. So there's a couple other times where we don't see experimentally what we expect to see. And it is consistent for our transition metals for groups 6 and 11. For groups 6 and 11, one of those s electrons will actually go into the d orbital. It's a little bit stabler, seems to have a lower energy state, and that seems to be what the elements tend to form more commonly. So we don't actually, for groups 6 and 11, we don't fill up the s orbital completely. We take one of those electrons to kind of either fill up the d for groups 11 or to half fill the d for groups 6. Now, we see this again with intertransition metals where they kind of go really, really wonky. There's not as predictable of a pattern, so I'm not going to expect you to remember them. AP College Chem typically doesn't expect you to remember them. So when you're doing your intertransition metal electron configurations, just follow our rules. Assume they play by the rules. If they don't, it's okay, because I'm going to assume they play by the rules. And if they don't, it's okay. So that is it for us today. I know that's a lot of information, but we are actually officially finished with electron configurations. And wrapping it up, tomorrow we will actually start trends. So we're still playing with the periodic table, but just know that if you need help, I'm here for you.